Thank you all. I'm going to talk about some work with Cavan, who's here, wave, and some of our other colleagues in Cambridge, and based on a lot of talking to a lot of different compiler people and systems programmer people and various others over the last several years. So we have to talk about C and what it is. And C is, it's kind of a fantastic kind of a beast, right? Maybe a bit like a large dog, like an Alsatian or a Doberman or something like that. If you're friends with it, it can be all warm and cuddly. And then, well, if you're not friends with it, it can be a bit mean. But if we ask exactly what it is, well, it's got a lot of different heads, this beast. And you know these quite well, but let me just spell them out anyway. So the first head, this guy, is the ISO standard. Let me try and do after lunch audience participation, always a challenge. How many of you have looked in the ISO standard in the last year? So, written by a committee, including some people here, with a noble goal to declare a clear, consistent and unambiguous standard that codifies the common existing definition and promotes portability. So this is good. But, like almost all industrial standards, it's a prose document, right? So you have 700 pages, or 1400 something, 1600 for C++, of text. And that text is, like any other piece of prose attempting to describe a subtle and intricate thing, almost inevitably it's imprecise and incomplete and ambiguous in some respects. And especially because it's prose, it's not executable in any way whatsoever. So I'm not saying executable as an implementation. That's not something one would expect. But it's not executable as a reference, right? As a golden reference for what the set of allowed behavior of some piece of C is and is not. So you can't compute that, and you can't compute whether some program has undefined behavior of any of the many different kinds. And that means you can't use the standard as a test oracle for compiler testing or analysis testing or anything else. So that we think is bad. And then it's not just prose, but it's quite subtle prose. So quite a lot of it is clear, if you're sufficiently expert, but quite a lot of it still seems to provide grounds for extensive debate, even among experts. That's not very good. So the second head, then, is the language that you people implement, and all of your colleagues elsewhere. So that is implicitly kind of well defined in the code of the compilers, but it's quite hard to investigate what that is. And it varies, right? So that's really why Cavan and I are here, and why we went to Euro LLVM earlier this year and talked to a lot of people to ask you in person what you think GCC currently aims to implement. And then the third head, arguably the most important, is out there, the code base of C in the world and the assumptions that it implicitly depends on. And that's even harder to investigate, because you can't go and ask those people. You can do a little bit running code with sanitizers and other tools to identify what it relies on, but it's quite hard to get much from that. And obviously the code out there is all buggy, because all code is buggy, and so one has to distinguish between the assumption, it relying on some assumption that may or may not be true, and some bad code. And different people have different notions of what bad code is. So, in reality, none of these is all that clear, and moreover they differ. Right? And that difference is obviously bad. Right? Has been bad for many years now. big arguments about things, subtle bugs, increasingly more subtle bugs as optimization gets cleverer, so on. So, what can we do that's better? So we are not compiler people. We probably know the least about GCC of anybody at this meeting. We are programming language semantics people, broadly speaking. And we think it is possible these days, maybe it wasn't when the C standard started, but now it should be possible to make a rigorous semantics for a quite large fragment of C. And we're aiming to do that. We've been working on that for several years, which is executable as a test oracle for small examples, and which, wherever ISO is clear and uncontroversial, really closely follows that. And then the places that it is not clear are mostly in this memory object model stuff. So for that, we're trying to understand what each of those three heads says, and ideally to reconcile these, right, to get somewhat closer to that. So we've done surveys of people and talking to people and building candidate models and writing tests and posing questions. So we now have, I don't know, maybe 100 different specific questions, each with some test cases. And in the later part of this talk, I'm going to ask you a small sample of those. And if anybody has the patience to be asked a much bigger sample, then we would love to sit down and talk to you in person. So that's what works best with this. So first, let me show you the good bit. What can we do? So if we want to define C more precisely, the way we choose to do it, which seems to be a viable way, is to translate it into a much simpler language. In fact, a special purpose language designed just for this. It's more or less a first-order lambda calculus with extra bells and whistles. And then we glue that onto a memory object model. So what does this do? So quite a lot of the bits, so here's a bit of the standard which is pretty clear. This is the definition of left shift, and here we have the standard text, and this will be too small to read, but it's got a lot of specific clauses. If the value of the right operand is negative, the behavior is undefined. So as part of the definition of the Cerberus definition of C, we translate every left shift into all of this core program, and that makes explicit each of these conditions. So there's, like, this condition here turns into an explicit test that this thing is less than 0, and if it is, we get this specific undefined behavior reported. So this part works very nicely, right? The semantics is readable, it is easy to make it match the standard, it does the right thing. I can show you. We'll try live demos, always exciting. Especially after this morning's fine example of managing a poorly working demo. So here is this C program. Is that big enough to read? Just about. Yeah. Naively, one might think it's simple, but of course, there's the lifetime of X, and there's the evaluation order of plus, and there's some implicit conversions, and there's some checks for overflow. There's quite a lot going on here. And so this, in our semantics, gets translated into this core program, which is making that explicit. I don't know if I turn off some things. You can highlight just the bit which is that plus. Somewhere in the middle of this, there is a plus, the core plus, which is on real mathematical integers. And around that are explicit integer conversions and tests for things being defined and what have you. At the beginning up here is an explicit creation of the object for X, and at the end is an explicit kill for the end of the lifetime of X. So this is making things quite nicely plain. I have to tell you some caveats. So A, it's work in progress. B, there's lots of things it doesn't cover by intention at the moment. But C, most important, This is really intended to be a reference semantics. It's not a bug finding tool, and that's a totally different aim. And to make one of those, well, A, you'd have to cover all of these things, but B, you'd have to make it perform much better, and that's at odds with making the semantics clear and transparent. So, I don't know, apparently it goes like 1 million times slower than GCC 00 at the moment. Right? And we think that's a good number. That's fast for this kind of thing. So don't imagine you're going to use this for debugging large programs, but you might use this for checking that test cases are free of undefined behavior. Okay, so now let's start talking about the more debatable things. So pointer provenance. So naively, pointers are machine addresses. And back, when God created this in 1970, that's what they were. And at runtime, well, they still are normally, but we have this beautiful-ish defect report and its committee response from 17 years ago now. Implementations may treat pointers based on different origins as distinct, even though they are bitwise identical. Okay, why? Well, probably most of you know. How many of you already know that why perfectly well? Yes, several of you. So your fine compiler is doing some alias analysis, and among other things, it is reasoning that two pointers that have different provenance, in some cases, are necessarily distinct. And that's used to license some optimization. And that optimization would not be sound if those aliasing facts are false. So if you have an example like this, so you make two objects which happen in this execution to be allocated adjacent on this particular implementation, and you add one to one object, and it just happens to end up with the same numeric value as the other one, can you then use that pointer to access the other object? Well, GCC 02 implicitly says, no, that would be bad, right? Because you get out some outcome that is different from what you would get with a fully concrete interpretation of the language, with a concrete memory model. But, licensed by this, we can cheerfully regard this program as having undefined behavior, because this access is to an object via a pointer that doesn't have the right provenance to access that object. Right? P starts out with the provenance of the address of X, with the provenance of the object X, and after that arithmetic, it still has that provenance, but here we're trying to use it to access object Y. More live demo recreation. Let's see if this works. So here's a slightly cut down version of that example. Basically the same. Here are pretty pictures of the memory state drawn by Cerberus. See if that works. Well, we create an object for X and we create an object for Y, and we we do the arithmetic. We store into X and Y. We create P, which initially has an unspecified content. We create Q, which initially has an unspecified content. We construct the value P. So this is now pointing into Y, and that is also pointing into Y, but this, it's shown in red just to kind of compress it because we don't want to show you all of the provenance data, but this is an illegal to access pointer. And when one tries to do that access, it says, oh dear, Okay, it says it in a very small font now. It says, oh, no, that was undefined behavior. Yeah? So the tool is correctly identifying that by explicitly tracking these provenances. So from your point of view, that's good, right? That licenses this alias analysis and optimization. Right? So this is the beginnings of trying to make this more precise. Right? And the basic idea is quite simple, that with every pointer value and every integer value in the C abstract machine, although not in implementations, obviously, you carry around a provenance. And a provenance is either an allocation ID or a token that says there is no provenance here. And whenever you do an access, you have to check that the provenance of the pointer used is legitimate with respect to some live object. Oh, sorry, with respect to the right live object. Otherwise you get undefined behavior. Yeah? So for this simple example, that's pretty straightforward, and it gives, as far as we understand it, the desired behavior. Now we look at some more tricky cases. So suppose you round trip a pointer via int pointer t and back. Should you be able to use that for accesses? Yes, I hope. Does anyone disagree? Not today. Good. So, and this is also consistent with GCC documentation, we make the integer values also carry provenance, and these casts preserve it. So far, so good. If you've got a pointer to one object and a pointer to another, can you get between them by int pointer t arithmetic? Can you, given constructing a pointer to x and an int pointer t offset between these two objects, can you add that offset to get a usable pointer? Well, probably you want to forbid that because you would like your alias analysis to be able to assume this doesn't happen. So that's fine, and it's easy to do in the semantics. You make the subtraction of values that have distinct provenances, actually at any subtraction, I think, have a result that has the numeric value you'd expect, but has an empty provenance. So that then becomes illegal to use for access. But when you start defining a precise semantics, you realize you're making choices all the time, right? And the choices have consequences. So here, this choice is also saying, you know, your friendly 19, I don't know when, ZOR linked list clever pattern is definitely undefined behavior, according to this semantics. Is that fine? Let's try democracy. It's always funny. Is that fine? Are we fine with that? Are we not fine with that? Fight, 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 fight. See, we here are largely trying to be sort of neutral, pure-minded third parties trying to make the world better. Right? In some sense, we don't have an opinion. Well, secretly we do. But, Florian, question. If you tell me 3 times.
Okay. I don't think it's defined, but we actually need this kind of stuff in the implementation of a C library. So that applies to a lot of these things. So it makes it hard to write a C library without violating this stuff.
So do you need some way to tell the compiler, please, let me do this right here? And do you have that way at the moment?
I think we could. We probably should just disable any kind of aliasing analysis for things that, at least for things that are addressable, and GCC supports that, but we currently don't do that.
When talking about implementing the standard C library, one important point is that we are very definitely writing in terms of C with ABI boundaries at present. So even things that may be defined on the level of the individual translation units, but are also required to interact with other translation units only according to the standard ABI, so that if the implementation starts doing link time optimization, there are definitely things that would go wrong in glibc, for example, because we're relying on the existence of ABI boundaries.
I would like to point out that the question at the header of the slide does not exactly reflect what the code is doing, because the question is talking about pointer arithmetic, but the code is doing arithmetic on integers.
The question is not specific one way or another. If you try writing these questions, it's very hard to write questions which are shorter than this long and entirely describe the code. So the question is more generic than this code.
Yeah, so this was recently discussed on the GCC Bugzilla, and I think the current consensus is that doing this on integers is well defined, and GCC actually gets that correct on tree-level optimizations, but then due to a long-standing historic bug, gets it wrong on RTL optimizations, but that is accepted as a bug. So the current consensus seems to be that the code on the slide is well defined, and so is XOR arithmetic.
Okay, interesting. Surprising to me. Interesting.
We also have the Bugzilla discussions of the related question about whether the comparison, whether if instead of memcomp you do a direct comparison for equality for the pointers, whether the point of equality comparison needs to have consistent results. Yeah. Because you have this thing in the C standard saying they compare equal if it's the same object, or it's the object one after an object and another object that happens to come immediately after it in the address space. So my view, as explained in one of those discussions, is there is nothing in the standard that says that the property that this object comes after that object in the address space has to be runtime constant throughout the lifetime of those two objects.
So that I think we have to argue about offline, because it would take too long. Can we go to the guy in orange?
Your concept of provenance isn't rigorously tracking what the C standard advocates. And in particular, you...
So the C standard, to sort of short circuit, the C standard says nothing about provenance. You use this provenance
the only
thing you
find
get,
undefined behavior.
Well, the only thing you get is this in the committee response of a defect report 17 years ago. That's it.
Well, you can use arithmetic to mask a pointer value. So you can convert a pointer to an integer, and then you can do some arithmetic that, depending on some other inputs, either yields the original pointer value or the value 0.
Yeah.
And you can combine two such values with XOR. And as I understand it, your scheme will give us 0 provenance, even so it is always a valid pointer as long as exactly one of the inputs gets through and the other one gets masked to 0. And this is not computable.
I think that's correct, yes. Yes.
In general, it's not computable if some calculation performs such a mask operation.
Exactly, and this is why we think that a reasonable, usable semantics has to be approximate in some way with respect to the numeric values. Also, I mean, the alias analysis won't be able to, you have to have a reasonable bound, a reasonably simply definable bound for what alias analysis is allowed to do, otherwise you're doomed. Well, maybe we are already doomed, but let me continue now.
Forbidding things that should be allowed.
Let me continue. Yeah, so this may speak to your question. So storing information in otherwise unused bits of pointers. The C standard is quite unclear about this, but real code relies on it all the time. It's surprisingly reasonably straightforward to make a precise provenance semantics that allows this by, I'm not going to walk through all this code, but just by taking care to make these bitwise operations preserve provenance in the right places. That seems relatively uncontroversial, except...
This point links into, well, a different controversial thing, namely, if you malloc something of size 1 byte, for example, does it still have to be suitably aligned for objects of larger sizes? And well, there's this C90 defect report response that says, yes, it has to be aligned for any type of object. And doing this sort of trick is basically the reason why requiring that from malloc is useful, because then you know you have these low bits. But plenty of malloc implementers would rather not require your 1-byte allocations to be 16-byte aligned, because that wastes memory for everything that does not use this trick.
Yeah. So you have to make a real choice. Okay, so one of the lovely things, one of the fascinatingly delightful things about C from a programming languages person point of view is this fact that you get access to the representations of everything. And so a reasonable provenance semantics has to make memcopy of a pointer value actually work. And it should work even if the user writes their own byte-wise memcopy rather than using a built-in. So that's what this code is doing. It's just copying a pointer, but byte-wise. How do we make that legal? Well, we regard each of those bytes as an integer value as carrying the provenance of the original. And when you come to reassemble the pointer value, as long as you don't have any conflicting provenances, that's fine. No problem. But choices. Right? So if we are forbidding inter-object arithmetic and the XOR stuff, then we are also making undefined code that encrypts together a whole block of pointers. So it's using exactly those same operations, and then decrypts them, and then tries to use them for access. That's not a very common thing, but it does happen. So maybe the language, again, needs a way to tell alias analysis that it's doing something strange at that point. Who's got the microphone? Microphone?
I'm not sure practically it needs an escape hatch for that for implementations, simply because it's like outputting a pointer and then reading it back in. The address of the pointer is being taken and it's manipulated in such a way that the implementation can't tell where it came from.
Well, so that leads us to this, which is a very interesting question. So if the implementation thinks it can't tell where it came from, then exactly what bounds does that imply on what it might alias with? If I read in a pointer value, we could say it might alias with anything which I have, which has escaped by I/O. That would be a pretty tight version. You can't always tell from the code that that's what's happening. Or at the opposite extreme, you might say it can alias with any object which is live at the time you use that pointer for access. So that pointer might not have even existed. That object might not even have existed at the point of input. So if somebody can tell me what GCC is it in practice assuming in this scenario, then I would be a happier man. Well, depending on exactly what they told me, but I think I'd be a happier man. Well,
depends on which way you get the value back in. So in the old style precompiled headers, you basically got this into block allocated memory. So you don't
sorry,
know
I
the
can't hear.
Yeah, this writing pointers out with I/O and reading the back in. That happened actually with precompiled headers. We removed them since, but yeah, we had them.
I'm sorry, I'm not understanding.
We used to have precompiled headers, which basically just wrote out all the heap, including all the pointers, and then read it back in when you use the header. So you got lots of pointers there, but because they're in the heap, the implementation doesn't make any assumptions what kind of pointer it lives there. So the type sort of depends on how it's used.
I would be surprised if such a pointer was immune from, for instance, attribute malloc, which says definitively that we are allocating a new object. So the compiler could reasonably reason that whatever pointer you had gotten from I/O is not within the new object that was just returned. It seems likely that at best it would simply drop down to type-based alias analysis and not attempt to reason with provenance beyond that.
So you don't think, for example, that it would reason that a pointer that you input, let's say you input with %p, this is like the easiest case. So suppose you input with %p and then create a local scoped thing. You don't think it would reason that whatever you input is distinct from the locally scoped object that you created after the input?
Yeah, I don't know.
The objective of the compiler is not to break all programs that don't conform to the standard. It is to correctly compile the programs that do conform to the standard.
But the question here is fundamentally ambiguous because the standard doesn't say. That's the point of all of this work. If the standard was totally crystal clear, we wouldn't be doing this.
In the first place, if the compiler can't tell that some optimization is safe, then it must not do it.
Okay, but safe depends on what you think the ambient definition is, which we don't know.
In the first place, a pointer that has been read with I/O might be identical with something that has a valid provenance.
Yes.
So the compiler must assume that it's valid in any possible scenario where it might have been obtained with a valid provenance.
Okay, I'm not sure that resolves which of these or other choices we should be picking. Let me move on, because there are lots of interesting questions here. My goal here is clearly not to reach a conclusion, but just to kind of raise some awareness and get people talking to us about this stuff. So here's a lovely example that came up in earlier this year when we went to Euro LVM and talked to lots of interesting people. So here's some code, and we create an object, and we create a pointer to that object, right? And let's just suppose that it's allocated at that address. And then we cast it to integer. Okay, so we've still got something with that numeric value and that provenance. And then we bitwise and that. Well, we've still got that numeric value and that provenance. And we bitwise and that again, speaking to your earlier point. And now we have that value and that provenance. Okay, but so as a consequence of the fact that we're choosing a relatively straightforward semantics for these provenances, and one which is computable and has other nice properties, if you then add on this number which you just guessed from the top of your head, you get, well, something with the right address and the right provenance that in our semantics you can then use for access. So this is not in itself desirable. It's not especially undesirable that the semantics permits this, except, as Richard Smith pointed out to us, well, alias analysis may be happening after some algebraic optimization, and it might replace all of this calculation up to here by just 0. And therefore it's lost a representation in the internal language that that may in fact depend on a thing with the provenance of X. And therefore alias analysis may assume that it definitely doesn't alias with that thing, and therefore there may be some unsound, concrete model unsound optimization. So that's bad. And there seem to be two things one could do about it. So one thing, so if you're in an implementation that is in any case taking a pretty conservative view of pointers that are constructed from integers, assuming that they can alias with almost anything, then this is no problem. If you have an implementation that does not assume that, as I believe, but you tell me, GCC does not, then maybe one would need to do more work to, and maybe it's a feasible amount of work, again you tell me, to record in such optimizations the things that they erase, the dependencies that they erase, not to affect code generation, but to explicitly tell alias analysis that it should remember those dependencies.
Looking at this example, it strikes me pretty similar to the case of doing pointer arithmetic on a null pointer. So,
well, this is, I mean, this is not a null pointer.
yeah, but after compiler optimization, you might
then it
end
looks
up,
like one, yes.
yeah, and then it's complicated. Yes.
The last time I've seen this in GCC, it was just using an alias set that says may alias anything.
So if it's doing that,
Just doing
then
it's a conservative thing when you don't know.
GCC will happily optimize this, determine that X no longer has its address taken, and remove the addressable mark on the variable. I would be very surprised if this works.
So certainly, in principle, the optimization saying that that thing has got I3 is 0 is valid if you've got a code model that says that addresses are in the low 32 bits or whatever. I'm not sure if GCC does that. And then for the other thing, guessing the address, well, there are contexts in which GCC is used in which that's legitimate. That is if you're building for an embedded system with a linker script that is placing objects at particular addresses. But one might plausibly expect that you disable this part of alias analysis if you are placing things at particular addresses like that when building for an embedded system.
So I'm not so concerned with code that is intentionally doing this. Right? The point of this example, as far as we're concerned, is that it may make it challenging to, in general, correctly implement the otherwise nice and simple provenance semantics that we're proposing. Because, I mean, that has to work for arbitrary code, including code which includes a guest address, even if it's not natural code except in the embedded circumstance.
If GCC can act default these to end operations and sees a 0, depends on host and target bit sizes, so the target address size and the host integer and long sizes, and some further pieces of GCC configuration. So the answer might actually be sometimes.
Subobjects. Subobjects are fun. The ISO text doesn't really know the word subobject. Sometimes when it uses the word object, it might mean object or subobject. Sometimes it probably doesn't. So this is a thing that the proposal I've sketched so far allows, and probably one shouldn't allow, because we've so far only done provenance at the granularity of whole allocations. If you make a struct with 2 members and do arithmetic between those two members, that is in the proposal so far, allowed. Probably you don't want that. Do you want that? Or rather, the more interesting question is, does the existing implementation already strongly assume that code is not allowed to do that? Nobody wants to speak to that one. That one. Here's a question. So Martin,
You're certainly allowed to compare these values.
sorry, say again?
You're certainly allowed to compare these values, but
Yeah.
what you get is a different question.
I think if you compare, sorry, I'm not comparing the values here. I'm only checking the representation values of the pointers are equal.
You compare the bitwise representation of these values. You're comparing the bitwise representation of these pointer values.
Yeah.
That much you're allowed to do.
You're certainly allowed to do that. Because it's just a representation bytes.
You're allowed to start with P, or you're allowed to not start with P. So it's still valid, but you can't assume any particular outcome.
When you're doing stuff with sub-objects, you also have the type-based alias analysis questions for them. And the questions about pointers to members of unions and defect report 236. Then you've also got things like there was some set of questions about what is an object in connection with sub-objects that Nick McLaren posted to the Reflector around 2001.
Yeah, there's a whole world of sub-objects, which this is only the toppest tip of. Let me try this one. So here, you've got a struct. You make a pointer to one member, pass that around. Here you cast to the first member. Here you cast that to a pointer to the whole struct, and then use that to access some other member. A question beloved of Martin. So when we read the standard, we find this nice sentence. A pointer to a structure object suitably converted points to its initial member and vice versa. And then, well, so some people tell us that they have compilers which assume that this doesn't happen. And a considerable number of programmers talk to us and say, we do this all the time. They'd better not break that. And so I thought it would be instructive. Let's try, again, the democratic approach to language design. Is this currently in GCC allowed? Yes. Can be, you could tell a programmer writing in code that will be compiled with GCC, you can do this, it'll work, it'll be fine. Peace, Martin, later.
I was just raising my hand to vote. Is it allowed?
Okay. And not allowed. Okay, interesting. And not sure. And don't do this audience feedback stuff after lunch just anyway, on principle. Microphone.
The other way to ask the question would be, does it happen to have the intuitive outcome, rather than is it guaranteed to work? And I would have voted yes for the first question. Does it happen to have the expected intuitive outcome? I don't think it's necessarily quote-unquote guaranteed to work. I don't think it's spelled out anywhere.
Yeah, so the next or related question that I should ask is, what do you think GCC should be guaranteeing, or maybe what do you think C2X should be guaranteeing? Let's ask it again for that question. C2X should guarantee this works? Yes.
Can I clarify the question? Does it depend on whether that struct definition is there at the top? Whether F has an alias violation? Oh, I suppose it has to be for the body of F anyway, doesn't it? Yeah.
It has to be in scope somewhere.
So in this case, you know that it's possible that some ints come from one of these structs because that struct has an int member. Because there are other cases where it's supposed to be dependent on what's been declared or not, and that just seems crazy.
So there were several that said C2X should permit this, and people who say C2X should not permit this is sort of a equal number of people. There's democracy.
There's existing code out there that actually uses a similar construct to ascend to an enclosing super object. Yeah. And if we allow that, then that has to be allowed as well, because it's just using zero offset in some sense.
Yeah. Okay. How are we doing for time? Any more minutes? How are we doing for fullness of brains? We're doing quite well for fullness of brains. Let me just so we could go on like this for a long time, but let me talk about initialized values just quickly. So we did this survey in 2015, trying to target various mailing lists. You might have seen this, but trying to target only sort of people who are likely to be expert programmers in one way or another, not totally random C programmers from the internet. And one of the questions was this: if you try reading an uninitialized variable or struct member, do you get undefined behavior, or something that makes the result of any expression involving the result unpredictable, or some arbitrary but unstable value, subtly different, or some arbitrary stable value? And like many of the questions in this survey, we had a bimodal response. Lots of people said that. Lots of people said that. Probably neither of those are what your compiler does. So in practice, well, there seems to be some consensus. So reads of entirely initialized variables, they seem to be regarded as basically always programmer errors, except in some cases where people incrementally initialize bits of integers. Yeah, boo, sucks. And we certainly do see unstable results for repeated reads in some compilers, but it doesn't seem necessary for compilation or terribly useful for programmers to have totally arbitrary behavior in those cases. Right? Real UB. So then you turn to the ISO text. Sorry? Yeah?
If the values are unstable, how can you get predictable behavior at that point? Because that's sort of...
Well, there's a difference between getting an unpredictable value and having entirely unpredictable behavior.
I don't think so, because if you're an optimizing compiler, it assumes equality between values, and that assumption is broken by...
Well, I'm talking about the programmer level semantics. Right? So I can imagine compilers that would give you one but not the other. You look at the ISO text, and frankly, on this, it's kind of confused. So there are trapped representations, which have nothing to do with traps. And as far as we can tell, after discussion with many people, including some of you, the only current common implementations that actually have trap representations, the only case seems to be underscore bool.
Two. And there's also special hardware where you have error checking, so that if it's in the wrong state, you have to initialize it first.
But it's not the same. Yeah? So.
Parity error.
So the NAT bits were only attached to registers, right? They couldn't exist in memory. But trap representations, if you read the text of the standard, are quite explicitly concrete object bit patterns which can live in memory. So it might be that this was introduced partly because of the Atanium NATs, but what the result in the standard text as written isn't that. So then we ask WG14 people, and some of them believe that the intent of the standard is to make uninitialized reads at non-character type always undefined behavior. And so that's clearly not what the text says, but some of them assert that that is the intent. What should it be in C2X then? So there's a lot of options. And you might well say, well, the default for our compiler should be such and such, but there should be an option to give more predictable results in security critical code, where actually you'd rather not have any arbitrary values, thank you very much. You would rather that the language standard requires that when you read such and such, you are not given your SSH key value from somewhere totally different in the program. That would be a comforting kind of requirement for the standard to state. I kind of guess that your compiler at the moment does C, but I don't know. No?
I think that comes back to my earlier point then, because if you don't have stable reads and the language says reads are stable, then the language semantics no longer apply.
Yes, because the thing is maybe different if you read again. What's written in the source code as one read can, after some SSA optimisations, end up as two different values in two different bits of the code coming from what was originally one read.
Okay, so all that code which is doing incremental initialization of bits is just bad according to this notion, because that is UBI, you're saying.
Well, I suppose in principle it should be able to have a read return different values, but all those values will have those particular bits that have been incrementally initialized. But that's what it would behave like in practice. How you'd represent that in the standard, I have no idea.
Yeah, I think you don't want to represent that in the standard. People have tried. There are academic papers trying to do that, but it's a bit nasty. So then let me end. If we think that's undefined behavior, so if you have a struct which has some members uninitialized, and you try and copy that as a whole, should that also be undefined behavior? Ah, I see differential shaking of heads in different directions. Yes, be careful of the back of your neck, because it's easily damaged by rolling the head around too fast. So we're not going to talk about these, but there are many other interesting questions. Zombie objects. Maybe we should end with zombie objects. Yeah. Can you inspect the value of a pointer to an object whose lifetime has ended? So in this, the standard is totally clear. At the end of a lifetime of an object, all pointers to it, wherever they may be in the universe, magically, instantaneously take on the indeterminate value. But, well, hey, the sanitizer folk tell us that they very carefully have to not flag errors for that, because they find code is doing it all the time. And there's no way they could get all those people to change their code.
We specifically had to fix C++ for this case because it's very common, shared pointer and weak pointer. The whole point of weak pointer is that it continue to exist and tell you if the thing that it used to point to has expired. And you can still copy a weak pointer after the thing it used to point to has expired. It doesn't become radioactive because that would defeat the whole point of it. So C++ makes a different choice of saying that you can't indirect or try and delete the pointer after it's become invalid. Everything else is implementation defined. So, and that basically means if it becomes a trapped value, or you have a system where once it's deallocated memory, even copying it would blow up, that then becomes implementation defined. But all sane implementations and sanitizers will still let you copy it around. And this is really quite restrictive, the C rule. Yes, it is a pointer value, yeah. Because we had, we realized that there were millions of lines of real code that were doing exactly this all the time in a type that we told them that was good for keeping hold of, it still works after the lifetime's ended.
Yes. So I think I'm also chairing myself, so I should tell myself that I only have almost no time.
My expectation would be, so if you compare this end pointer to something whose lifetime has ended with, say, a pointer to a newly allocated object, that might sometimes produce true and sometimes produce false, and like an uninitialized object, a single comparison might produce a result that sometimes acts as true and sometimes acts as false, after optimisations have duplicated the comparison and optimised it differently in different places and so on.
We're not going to start talking about effective types now. Shame. But they're really interesting. Or padding. Shame. Lots of questions about padding. Yeah, so, well, this is kind of obvious. It's kind of disturbing that we still have this lack of clarity about some pretty basic questions. But we think it is possible to do better. So please do and come and talk to Kevin and me. We're around until tomorrow afternoon sometime. If you would like to go through some of these questions more systematically, either with us or offline, then let us know. And maybe we'll make a more fluffy, happy world. Thank you all.